subset of points are linearly independent. Okay, so here, for example, I have 3 points. So I demand that each subset of 2 points is linearly independent, meaning that I don't have 2 points that rely on the same straight line. Okay? For example, this set is not in general position because I have a subset of 2 points. It's even more general than that. This is an example for points which are not in 2 dimensions. It's relatively easy.
Well, in 2 dimensions, every 2 points will be collinear.
Would be no, in 2 dimensions, if the 2 points are not rely on the same vector that goes from the.
I mean, if
this is not good. Okay, this is fine. Why?
Yeah.
What is the definition of linearly independent in 2 dimensions? 2 dimensions is. So the definition of linearly independent is if you're taking this mu alpha mu and you want it to be 0, then if the points are linearly independent, it means that the only way to get 0 is with coefficient 0. Okay? So if the points are linearly dependent, for example, like this, you don't have the alpha that doesn't have to be 0 because, for example, if mu x1 is 1, 1, x2 is 2, 2, okay, I can choose alpha 1 to be minus 2, alpha 2 to be 1, and I will get 0, right? So it means that these are on the same vector. In 2 dimensions, it's easier to understand it.
Okay.
Okay?
Yeah.
משהו בהתחלה,
כן.
אני החלטתי שהם התיוגים שלהם?
לא, זה לא התיוגים, זה כמה. אוקיי, גרופ 1, זה אומר לי דיכוטומיות כמו הירוק, שעבור הנקודה החדשה ששמתי, אוקיי, היא יכולה לכל רק שיעור אחד. היא חייבת להיות שיעור. לפי אחד אומר לי כמה דיכוטומיות כמו הירוק יש לי. אוקיי? בכמות. כמה כאלה יש לי עבור השלוש נקודות. אוקיי?
חשבתי שזה כאילו מאוד שלא קשורות.
אוקיי.
ואז... אז למה כאילו... למה זה 2?
בגלל שעכשיו אני מתחברת לנקודה הספציפית של פיפלוס 1, אני הוספתי עוד נקודה, ואני בודקת כמה דיכוטומיות אפשריות יש לי, כמה תיוגים יש לי לכל הסט הזה, שיכולים להיות מתויגים הפרדים ליניאריים. חשבתי, אבל אני מחפשת את פיפלוס 1, מה זה איך הוא קשור לפי. אז אם אני לוקחת את... כאילו כאן נוסף כל תיוגים יש לי, כאן באפליקציה פי, נכון? כן, כאן באפליקציה. אבל לא כל התיוגים האלה יכולים להיות ממומשים על ידי הפרדה ליניארית. נכון? אז עכשיו אני רוצה לדעת כמה יכולים להיות ממומשים. עכשיו אז בעצם, במקרה הזה, כאילו, זה המספר של 3 נקודות יכולים להיות ממומשים. נכון? גרופ CPN, במקרה שלנו C3, 2, אומר לי כמה תיוגים יכולים להיות ממומשים על ידי הפרדה ליניארית, כי יש לי 3 נקודות ו3 מימדים. נכון? בשני מימדים. עכשיו אני רוצה לדעת את זה.
כאילו אם תוסיפי עוד נקודה.
הוספתי עוד אחד. אז בעצם הדרך שלי להסתכל על נקודה, אם הנקודה בשייכת לגרופ 1, היא בעצם, יש לה רק תיוג אחד אפשרי, נכון? אז היא לא הגדילה לי מספר התיוגים שיכול להיות, אז אני פשוט לוקחת את גרופ 1. נכון? יש לה רק תיוג אפשרי. אם נכנסת לגרופ 2, היא בעצם מגדילה לי אז על כל תיוג אפשרי של גרופ 2 יש לי שתי אופציות לעשות תיוג חדש, נכון? כי אם אני באדומים, אז על כל...
מה זה אומר שתי אופציות?
שתי אופציות, הנקודה החדשה, אם היא באדומים, צריכה או פלוס או
היא יכולה להיות או פלוס או מינוס.
היא יכולה להיות או פלוס.
אבל מה זה על כל תיוג?
אז על כל אדום, על כל אדום, אני יכולה לתת לה שני תיוגים. נכון? על כל תיוג ששייך לקבוצה האדומה, על כל תיוג ששייך לגרופ 1, ותיוג אחד ששייך לגרופ 2. מה שציירתי פה?
לא הבנתי את המשפט על כל אדום.
על כל תיוג ששייך לקבוצה 2,
כלומר,
כמו האדום הזה, פלוס או מינוס לכולם, לקבוצה הקודמת של 3 נקודות, הקבוצות הן רק של 3 נקודות.
אוקיי.
אז אם היא שייכת לגרופ 2, על כל תיוג, אני מקבלת שני תיוגים חדשים, נכון?
לא הבנתי, עכשיו לזה יש לך שני תיוגים?
לא. הוא מוסיף לי שניים, זה יכול להיות איפה אדום? הוא יכול להיות פלוס ומינוס, זאת אומרת שעכשיו יש לי שני, כאילו, לכל כזה, הגיעו לתיוגים של אלה, יש לי שני תיוגים אפשריים לא, נכון?
כן, אבל לכולם ביחד, לא לכל אחד בנפרד.
בסדר, יש לי שני תיוגים אפשריים לא, ולכן זה הוסיף לי שתי דיכוטומיות שאפשר לתייג אותם. עכשיו אני עוברת את כל התיוגים האפשריים של הנקודות, ואני מספרת כמה מהם אפשר לתייג.
כן.
אז איך אני עושה את זה? מה המקסימום שאפשר יהיה? המקסימום זה כפול 2, נכון? זה לקחת את הקודם כפול 2, זה הכי הרבה שיכול להיות לי.
כן.
נכון? זה נגיד שלכולם יכולתי לתייג את הנקודה החדשה פעמיים, זה הכי הרבה שיכול להוסיף, אבל יש לי פחות מזה. כי עבור חלק מקודם אני יכולה לתייג אותה רק פעם אחת. אז יש לי פחות זה צריך להיות קטן משני CPN. נכון? זה צריך להיות קטן מזה?
אוקיי.
כי הכי הרבה, כאילו קטן שווה. אבל עכשיו אני בודקת איך זה קשור לזה.
אתה רוצה לעזור לי?
אז אם אני CPN אני יכולה לחלק לגרופ 1 וגרופ 2, נכון? גרופ 1 זה דיכוטומיה, זה אומר זה אלה שעבורן הנקודה החדשה יש רק תיוג אפשרי אחד. נכון?
כן. כאילו, סתם בחרת רק 2, נכון? כאילו, הייתי יכולה לעשות כמה.
לא, איזה עוד מלא יכולתי.
זה
לא, מה שציירתי פה זה דוגמה, יש לי רק שתי קבוצות אפשריות, ציירתי דוגמה מכל קבוצה. ציירתי דוגמה אחת מכל קבוצה. אני יכולה לצייר עוד דוגמה של דיכוטומיה לגרופ 1, דוגמה אחרת. אני מבינה, ציירתי דוגמה אחת, אבל יש לי רק שתי קבוצות.
כן, אבל זה
אוקיי, זה רק שלושה תיוגים אפשריים. זאת אומרת, הכי טוב שיכול להיות זה
לא
שניים.
הבנתי.
אף פעם לא יכול להיות, לכל נקודה יש שתי אופציות, פלוס
נכון.
ומינוס. best case scenario אני יכולה לבחור נקודה גם בפלוס וגם את המינוס.
בהינתן
בהינתן
התיוגים
התיוגים
אבל תוכל
האלה.
לתייג את זה
נכון,
בדרכים אחרות.
אבל עדיין הם ישתייכו או לפה או לפה או לפה.
כן, אבל אלה סתם דוגמאות.
כן.
כאילו, זה באותה מידה יכול להיות פלוס, מינוס, מינוס.
כן. הירוק זה דוגמה אחת, היא דיכוטומיה ששייכת לפה, והאדום זה דוגמה אחת, היא דיכוטומיה ששייכת לפה.
ואז, כאילו, שוב, אז למה זה 2?
אז למה זה 2? כי זה מוסיף לי שתי דיכוטומיות אפשריות, וזה תורם לי דיכוטומיה אחת.
כאילו שני תיוגים אפשריים?
שני תיוגים. כן, אבל שני תיוגים אפשריים זה אומר לי שהוספתי שתי דיכוטומיות בארבע נקודות. קיבלתי שתי דיכוטומיות בארבע נקודות. תיוג אפשרי אחד, קיבלתי דיכוטומיה אחת בארבע.
דיכוטומיה זה כאילו
דיכוטומיה זה אוסף פלוסים ומינוסים. כאילו, נתון לי המיקום של הנקודות, ואני בודקת כמה דרכים יש לי לשים פלוסים ומינוסים, כך שאני יכולה לשים מפריד לינארי. כן, כל האפשרויות
של השיעורים.
נכון, שהשיעורים שלהם אפשר להפריד לינארי.
ולמה זה כאילו השלב הבא?
בגלל שהם...
אבל זה רק בשביל השלב
מה, זה לא נשאר... נכון? לא, זה ציפי פלוס אחד. עכשיו אני מציבה את ציפי.
אוקיי.
Yeah, that's what I mean.
No, you mean after like that?
Yeah.
And then there's
1 month.
yeah, it's also two machines next to it.
אוקיי.
And then get in, and then there's only one more.
I don't know, but it's too much, like when you're having these extra classes.
מה עדיין לא
לא,
עושים? אוקיי.
When I was in elementary school, I could do it, but now I can't. I'm serious.
התמודדת בזה?
כן, זה ממש כאילו הכי טקסי בעולם שלב הזה. זה בקטע הזה של למה זה מוסיף 1 ולמה זה מוסיף 2.
אז אני חושבת שעתיים כדי...
לא, הבנתי את הקטע של כאן יש לך עוד 2 אופציות שאת יכולה לקחת.
כן.
אז אני חושבת שכאילו הבעיה... סתם, ההגדרות פה קצת מוגבלות.
הן מוגדרות זה לא הגדרות ברור להבין. זה מאוד מוגדר היטב, אין פה הומופוביות ומה זה אומר? ההבנה למה זה אומר היא לא אין פה איפור. זה פשוט כאילו קצת
לא, אני לא חושבת שיש תוכן איפור.
אבל צריך
בהצגה שלו יש איפור.
צריך קצת לחשוב על זה ולהבין את זה. אני לפחות ליורם שבוע. יורם, עשיתי להם שעה, צריך לחסר להם ברבע שעה.
יופי, סליחה.
כן, דימה.
לא אפשר לך לדבר.
יש לי שאלה.
להתקשר אליי, טוב.
מוכן שתדבר אותה.
לא, חשבתי לא. שכבר סיימת כבר שלפות, תגידי להם. טיפול, זה לא יודע, איך מטפלים מה זה. זה לא רק טיפול כאן.
Then, just to move that,
תראה, אני מניח שחלק ראשונים באקדמיה, אבל... אנחנו לא רוצים לשם יותר פרקטיקה. קשה להכניס את הנקודות.
שאנשים הולכים לפני לימודים יותר אוניברסיטאיים, אז יש לו רצון לעזור לאנשים, אל מול הידיעה שזה מרוויח מספר הרבה סדרתיים שכל החיים שלך הולכים לטוב. זה נורא מעניין.
זה במקרה הטוב, לא היה אף פעם זה
אם אין לך עבודה, לא לפעמים.
לא, דווקא העבודה יש. אני לא חושב שזה יותר... לא, דווקא לא.
באמת לקהל הזה את השאלונים האלה. אני מכיר אותם. אני רוצה לעזור כל הזמן, לא.
טוב, לא, זה ארטיפיציאלי.
זה הפוך מההיגיון.
זה בדיוק עבודה סוציאלית. אבל אני לא מאמינה גם ככה בשאלונים האלה.
בסוף תצטרך לפנליזר את אותו רק לסבך אותה. היא תוריד את כל המבדקים האלה.
הנה, היא עבודה.
נראה, נבדוק את זה.
או שכן, או שכן.
I would like to first just clarify notation just so that we will not confuse ourselves. I will use the term linear perceptron for y equals W transpose X, just learning of a linear real number and the binary perceptron for what we're discussing now, what we started last time. Y is equal to the, sorry, this was like this, and this is a sign of W transpose X. Okay, so this is what we're discussing, and so the architecture of our network is inputs X that feed into a single unit with linear weights, and the output is 0 or 1. It's the sign of W transpose X. And this is a way to, and we want to use this network to approximate a certain dichotomy, or maybe calculate it exactly, which we also want to learn from examples. So the structure of the function that we can implement is any function that can be described by an n-1 dimensional hyperplane which goes through the origin, and the function is 1 on one side of this hyperplane and 0 on the other one. And we decided to calculate the capacity, which is the number of different dichotomies that can be realized by such a function for a particular set of points on the plane. So we have p points, p examples, n dimensions, and we defined the capacity, again, as a number of different dichotomies that can be implemented. We are also assuming that the p examples are on a general position. So as I mentioned to you, and as you saw with Neta in the proof, one can calculate the number of dichotomies that can be implemented, and it turns out that if p examples are on a general position, the answer does not depend on the examples, on the specific position. Okay, so we can define something that we call CPN, and now covers which will be this, the capacity. And Kappler's theorem tells us that this is equal to 2 times the sum over k, for k going from 0 to n-1, p minus 1 over k. Now, note that k here, if n is larger than p, p minus 1 can be larger than what we have here, and then we just define this as 0, okay? So this is the convention. When I write this, the convention is that m over n is 0 for n larger than m. Okay, now, so before we discuss, actually, I mean, the proof you saw with Neta, but I want to start with just several very simple examples just to see that this formula makes sense. I don't know if you did this with Neta. You did it? Did you go through some examples? No? Okay, so let's do it. So let's just start with a classification of 1 point. How many dichotomies can be implemented by a binary perceptron? 2, right? So both dichotomies can be implemented. You just choose the plane, whatever you want. In this case, in my example, n is equal to 2. So our hyperplane is a line, and you can choose the value to be whatever you want. So C is equal to 2. And let's check this with this formula. So this is P equal. This is P equal to 1. So what do we need to do? We need to do 2 times the sum k going from 0 to 2. So k going from 0 to 1. 1 over k. Right? So when k is equal to 0, we have here 1 over 0, which is 1. So sorry, it's when k equals 0, it's 0, and then when k equals 1, okay. So we have here k over 1, and when k equals 0, it's choosing.
0 over k.
Okay, good, thank you. 0 over k. So so it's really 2 times 0 over 0. 0 over 0 is defined as 1. Okay, this is our definition. Okay, so it's 2. Now let's add another point. Because when k equals 1, it will be 0 over 1, and this is defined as 0. Okay? And when k equals 0, it's 0 over 0. We define this as 1. So maybe I should add this to our conventions here, that 0 over 0 is 1. Okay, now let's check another possibility, another case where we have 2 points. So we add another point. So now P is equal to 2. We have both these points. How many dichotomies are there in general? There are 4, right? How many can we implement with a binary perceptron? We can implement all of them, right? We can put the plane here, and then both points have the same value, or we can put the plane between them, and then we can distinguish, and we can choose all. So C should be 4, and our formula tells us that we need to take a sum over k going from 0 still to 1 of now 1 over k. So we have 1 over 0 and plus 1 over 1. Both are equal to 1. So it's 2 times 1 plus 1, and we get 4. Now let's add a third point. And here, by the way, it's not obvious that if I take my third point to be on the same side of the origin or the other side of the origin relative to these points, we will get the same capacity, but we do get the same capacity. We'll check this particular case. So how many? So there are 8 different dichotomies. How many can we implement?
If those 2 lie on the same line, then they're not in general position.
So let's first ask, how do we divide our 2 points between any dichotomy divides the points into 2 groups, right? Into 2 groups, and then we have 2 choices. We can assign 1 to one of the groups or 1 to the other group. So in any position of the plane, we will divide, we'll have 2 points on one side and 1 point on the other side, right? And therefore there are 3 different possibilities how to divide our 3 points, and so it's 3 times 2. So we expect it to be 6. What? How can you see a way to? Okay, so this is in this particular case. Okay, maybe I drew it a little ambiguous. Let's put it our point here. Now it's true that you could have a case, and this is why I was saying it. Now it's not obvious that it will be the same for any choice of positions. If you would put your point here, you could have a choice like this, but still it will turn out to be 6. So you can try it for yourself. Okay, so we have our formula, and our formula says that we need to calculate sum over k going from 0 to 1, and now we have 2 over k. So this will be 2 times 2 over 0 is 1, plus 2 over 1 is 2, and 2 over, no, 2, what's going on here? And that's it. K goes from 0 to 1. So 1 plus 2, and this is 6. Okay, so everything is fine. And now the next thing that I want to do is discuss a bit how this formula behaves when the arguments are large. We have many dimensions and many examples. Okay. So behavior, most importantly, the behavior for large n. By the way, I see that in my notebook I have sometimes capital N, but I don't remember what I did last time. Do you use capital N or small n? Okay, it will be the same. Okay, I'll continue with small n maybe because this is what I have here. So behavior for large n. So what I want to discuss first. I want to discuss 3 cases. So imagine that n is very large. Okay, this is very different from what we did here, where n was 2. Large dimensional input. What can we say about this expression? So, in fact, the first thing that I'm going to discuss is the case p smaller than n. And in this case, we're not even going to use the fact that n is large. We can just sum up this. Sum. We have here c of p of n is equal to 2 times the sum of k going from 0 to n, but exact to n minus 1, but because this is 0 when the argument here is smaller than this, we can just truncate the sum here. All the other terms are 0, right? Now, this should be something familiar. What is this? Yeah, these are the coefficients of the binom. So this is really the 2 times 1 plus 1 to the power p minus 1. Because this is when we open this up, this is what we get. I mean, we get the coefficients and then times 1 to the various powers. And so this is 2 times 2 to the p minus 1. In other words, 2 to the p. So what does this mean? Okay, so again, the sum is over k going from 0 to n minus 1, but when k is larger than p minus 1, this is 0. Okay? So actually what we did here was we replaced n minus 1 by p minus 1. Okay, so this means that when the number of examples is smaller than the dimensionality, or even up to the dimensionality, and the positions are general, we can actually implement any dichotomy. Okay? Okay, so this is actually true not just for large n. This is always true. Now let's take the case of p equals n 2n. So this is a particular choice, but you'll see that we just get a simple answer for this case as well. So in this case, C of p and n is equal to 2 times the sum k of k going from 0 to n minus 1. Now, I will write p as 2n. So this is 2n minus 1 over k. And now, what I'm going to do is the following trick. So I'm going to rewrite this as 2 times half of a sum where I continue to go with k for larger values, and I'll just convince you that it's the same. Okay, so what I'm going to do, I'm going to write the same thing. K going from 0, and now I'll go up to 2n minus 1. And I'll have here 2n minus 1 over k. Okay, so why is this the same? Because we can look at the values of k. So we have here 2n values of k. And they are 0, 1, up to n minus 1. These are the terms that we had originally. And then we have here n going up to n minus 1. And you can see that for because this expression is the same when k is 0 or 2n minus 1, or when it's 1 and 2n minus 2, and when it's 2 and n minus 3, there's a matching term here. There are 2 matching terms here which are the same. So for each term that we had here, we just added another term which has the same value, and we divide by 2. Okay? Fine, but now this is exactly the kind of expression that we had here, right? And we can write down this thing as 2 times half times 2 to the power 2n minus 1. Okay, so what we get here is 2 to the power 2n minus 1. So what does this mean? It's not, right? How many dichotomies are there? I mean, how many dichotomies are there? 2 to the 2n, right? P is 2n, so the number of possible, in general, the number of dichotomies is 2 to the power 2n, and the number that we can implement is half of that, right? So let's just write this down. All dichotomies can be realized by a binary perceptron, and this half can be realized. Okay, so far what we know is that when p is smaller and up to n, we can implement all the dichotomies. When p is equal exactly to 2n, we can implement half the dichotomies. This is also exact. This is true for any n. And now the part where we will make an approximation is the case of p larger than, much larger than 2n, or much larger than n. So let's imagine that p is much larger than n. So what can we say about C of p over n? Again, we have the expression here. So how does how does this grow as a function of P? How does it grow as a function of P? All the terms, I mean, all the terms that we add here, when we add more, we increase P, goes like P to some power, right? The term in the denominator always goes to P to some power, P to the n, and P to smaller powers. So, therefore, C of P and n grows at most as P to the n. Okay? Small n. Now, I'm not proving it formally, but you can see this again. You can see this from this expression, because what we have here is P to, the largest term that we add is P to the n minus 1, and then it's still divided by various things, and then there are terms with P to smaller powers. Now, what should we compare this to? We've already done the comparison in these cases. What should we compare the capacity to? The capacity is a number of dichotomies realizable by binary perceptron, and it makes sense to compare it to the number of total number of possible dichotomies. So the total number of possible dichotomies is 2 to the n, right? To the p, yes, 2 to the p. And I claim that this is, when n is large, this is much, much smaller than this. And p is large, this is much smaller than this. Why? The easiest thing to do is to look at the log of this expression, right? N times the log of p, this is what we have here, and here we have p times the log of 2. So as a function of p, this increases linearly, and this increases logarithmically, which is much, much, much slower than now. Okay, so I mean, this is true, and when we take the exponent, it's very true. Okay, so
for a large n and a very, very large
yes, it's a large n and a p which is large compared to n. So what we conclude from this is that in this case, n is large and p is large compared to n, a tiny fraction of dichotomies realizable by a binary perceptron. Okay, so now we looked at these three particular cases, any p which is smaller than n, p which is equal to 2n, and p which is much larger than n, and we can already use this to have to draw a plot for how we expect the capacity to look like as a function of p. So let's imagine now, what I will do though is that I will draw the capacity not as a function of p, but as a function of p over n. Okay? So now, one is a position where p is equal to n, 2 is where it's equal to 2n. And let's imagine at first that n is some finite number and actually not too large. Then what we have from these expressions is that, and also what I will do here is that I will not draw the capacity itself, but I will draw the fraction of dichotomies that are realizable. So I divide here by 2 to the n. Okay? 2 to the p, thank you. Good. Okay, so we know that, and now I will use different colors. So we know that this is 1 up to here, right? This is what we saw here. And then we know that it's half at this point. And then we know that it somehow goes to 0 for large p. right? So, as you might imagine, this function really looks something like this, okay? But something interesting happens when we increase n. Okay, so this is for some particular value of n, and in fact, what I drew here is for a moderately large n. It's not for a very large n. Okay? Yeah. But as we increase n and we ask what happens to this function, you can analyze a bit more deeply what we did here and conclude that even if you're slightly above 2, you will go to 0. For any value of p over n which is larger than 2, when n increases, the fraction will go to 0, will approach 0. Okay? And before, it's also possible to prove, which I will not do, that as you increase n, the fraction approaches 1. So what happens when n becomes large is that this function becomes a step function. So this would be a large value of n. So this is n. This n is much larger than, let's call it n1. It's much larger than n2. And so this is what we in physics would call a phase transition. When we go to the limit of large n, what in physics we would call a thermodynamic limit, we have a discontinuity in some statistical property of the system. In fact, here it's not statistical; it's a precise statement for any general position. And it happens precisely at 2. Yes. So when n becomes very large, essentially you have a step function. Of course, if p is equal exactly to 2n, you will always get half as the number of realizable patterns, but you increase p just a little bit, and you sharply drop the capacity. Well, it's like this. It becomes. I mean, it's always 1 up to here. It's always half here, and it will be some, smooth, more like the green. I mean, the smaller n, the more kind of gradual this is. But the decay, the decay for large p always exists. I mean, this is. You can see it from this. That always, from when p over n is large, you will approach 0. Okay, so really, when I say that I'm discussing large n, what I mean is that if I'm interested in the fact that you eventually get a step function. I didn't prove it. I just what I showed you is the behavior here, the behavior here, and the behavior here, and I didn't prove to you that that over the crucial thing is that for any point on the two sides of this transition, you approach either 1 or 0 when n goes to infinity. We didn't prove it. Okay. So therefore, when n goes to infinity, a fraction of realizable dichotomies approaches 1 for p smaller than 2n, half smaller than 2n, half for p equal to n, 0 for p larger than 2n. Now I want to make some comments. So one comment is that all this depends on the fact that we assumed that the values of the function are chosen randomly. I mean, if we imagine a situation where we kind of draw randomly a dichotomy and ask, okay, so this is true This is just true. The number of dichotomies that can be implemented is this fraction. But imagine that you draw a random dichotomy and ask what is the probability that it will be realizable. And if you really draw it randomly, you choose the values of the function on each one of the points randomly, then the probability that you will manage to realize it essentially is 1 if the number of examples is smaller than 2n, and it's 0 if it's larger than 2n, when n is large. But this does rely on the assumption of random choices. So if, just a second. So if the examples are drawn if the functions that you're trying to, the dichotomies that you're trying to implement are drawn from some distribution which is non-random. So for example, points that are close by in space tend to have the same classification, or tend to have different classification, then maybe the probability that you'll succeed will be different. We're not discussing it. Okay? Just to keep this in mind. Yes? Yeah. So of course this is, yeah, that's right. So, but that becomes true when n is infinite. So, when n is finite, when you add 1, there will be but larger, there will be a strong degradation in your in the probability that you'll manage to do it. Okay, but you know, I think it's very difficult for us to imagine things in high-dimensional spaces in general. So I don't have a good intuition. Maybe there is a good intuition, but I don't have it. But yeah. Of course, the number of dichotomies is also huge when p is large and n is large, and p is equal to n. So we have a huge number of points. The number of dichotomies is very large. So there's a decrease, a very sharp relative decrease. It doesn't mean, I don't know, you know. Well, again, it doesn't become 0. As long as n is not infinite, it decreases sharply. Okay, but you will still, I think, in fact, you will still have a huge. If you look at what is the number of dichotomies that you can implement for p equals 2n plus 1, it will still be a huge number. It will just be much smaller than 2 to the n. Okay.
The raw number of dichotomies that you can implement shouldn't go down.
Exactly. It doesn't. In fact, it increases. Yeah. Okay. So another kind of vague comment is that this whole capacity is somehow a measure of how many different functions this architecture can implement. But I mean, this is related also to my previous comment that suppose that you want to ask something about generalization. Okay, so you implement a certain number of you implement a dichotomy based on a certain number of examples, and you want to ask how well are you going to generalize for other examples. So this, of course, will depend on the structure of the rule that you're trying to implement. On the statistics of the whether points that are close by are similarly classified or not. So I'm not going to discuss these questions deeply. But it is worthwhile to say that although the answer depends on the structure of the rule that you want to implement, there are some statements which are quite general that can be made about these questions, about generalization. We're not going to learn these topics here. This is a topic of statistical learning theory. It's very interesting, but we don't have time to discuss this in this course. Okay, so the next thing that I want to discuss is a learning algorithm. So now the question is, we know that when P is yeah, okay. Yeah, good idea. So 15-minute break. Okay. So the question that we want to ask now is, suppose that P is smaller than 2n, or we have a dichotomy which is realizable by a perceptron with a dimensionality that we're considering, and is there a way to find the weights that will realize this dichotomy? So it turns out that there is a learning algorithm that is guaranteed to work, and I will just present it to you. I will not prove the convergence. Last year we did it in the TA session. This year, due to lack of time, we won't do it. But if you're curious to look at the proof for convergence, it's easy to find it in the literature. So, but I will just present the algorithm. So, what we first do is that we start with some particular choice of the weights. Can be anything. Okay? And now we start updating our weights. So, in terms of notation, I will call WT the weights after seeing T examples. Okay, so we have P examples, we go through them one by one, and each time, based on some criterion that I will describe, we update our weights. And so the update at step T plus 1, which is based on the T plus 1 example, has the following structure. If yt plus 1 times, so we look at the following quantity. What is this quantity? So these are the weights that we derived so far based on all the previous examples, and now we apply them to the T plus 1 example. And what does this tell us? Sign, yeah, we look at the sign of this thing. So, okay. So what would I will write down it. What does it mean if this is positive? Right. So it means that for these weights that we have so far, we're classifying incorrectly this example. And so actually in this case, we do nothing. We don't update the weights. On the other hand, if the classifier is not classifying, the perceptron is not classifying correctly, if it's not classifying correctly the n plus 1 example, then we do update the weights. And the update is the following. Wt plus 1 is equal to Wt plus eta times yt plus 1 xt plus 1. And eta is some number, fixed number, which we keep fixed throughout the learning. Now, one thing to note is that this correction kind of makes sense intuitively in the sense that it increases the likelihood that we will classify correctly this example. It doesn't necessarily mean that after this correction our weights will classify correctly the xt plus 1, but it does tell us that, right, if we multiply this by xt plus 1, if we apply the new weights to xt plus 1, we added something positive to if yt plus 1 is positive, we added something positive to this product, and if yt plus 1 is negative, we add something negative. So we're bringing this product, the product of the weights, the new weight stands xt plus 1 closer to the correct, in the correct direction. Okay? Yes?
The learning algorithm, do you show the same example?
Okay, so I didn't mention this yet. So far, you might think that we just go once through all the examples. Okay? But this is not guaranteed to lead to weights that work, because sometimes, you know, we have weights that work up to some examples, but now when we update based on the new example, we spoil. Okay, but the theory tells us that in fact, if we cycle through the examples again and again, we're guaranteed, if the dichotomy is realizable via perceptron, we're guaranteed to find weights that will implement it. Okay, so this is what I will not prove. So, but let's just finish the statements. Okay. So I didn't yet finish describing what we do. So what we do indeed is that we cycle through all examples, and then we stop if no update within an entire cycle. Right? If there was no update in the entire cycle, this means that we found weights that implement the dichotomy, and then we stop. So the convergence theorem tells us that if there exists a W star such that y mu times W star transpose x mu is larger than 0 for all mu. So this is just a way to write that the dichotomy is realizable by a certain binary perceptron with these weights. Then the perceptron learning algorithm will stop or stop after finite number of steps. Okay. Okay, so now several comments. Let's first look at this eta. So typically in various rules, we will discuss later another learning rule for another related problem. We call this eta the learning rate, because it tells us how rapidly we're updating our weights based on how rapidly we're based on each example. Now, in many problems, not this one, in problems that are more nonlinear, the learning rate matters, and things can be shown to work when the learning rate is sufficiently slow. Because in a sense, when the learning rate is slow, we're kind of averaging over the examples. We're not going into various directions randomly. Everything is more controlled. But in fact, here, the statement, the convergence theorem, doesn't say anything about the learning rate. We can pick the learning rate as we wish. And I want to try to understand why that's the case. Any ideas why it doesn't matter?
Sorry, but what doesn't matter?
Why eta? Well, the choice of eta doesn't matter. Okay, very good. So it's a scaling statement. It's because everything is linear here. So I will write it more formally in a moment. But the point is that all the updates that we're making, you see, are proportional to eta. So we can and also the decision that our perceptron is making is just, it doesn't really depend on the scaling of the weights, right? We can multiply the weights by a factor and doesn't affect the decision of the perceptron at all. So we can always redefine our weights by dividing them by eta, and then it's like doing the perceptron algorithm with rescale with eta equals 1. What does change? No. Time doesn't change. No. It's exactly the same thing, right? I can think so. My point is, okay, you know what? Maybe I'll write it down. What? No, because when you scale the W's, nothing changes in the decision of a perceptron, right? Multiply all your W's by a factor, the perceptron does the same thing. So again, my point is, we can just redefine imagine doing the perceptron algorithm. Maybe I'll write it down first, and then it will be more clear. So imagine that we have. My first point is no dependence on eta. And a way to think about it is, imagine running the perceptron learning algorithm with some weights, W0, and imagine that we start with W0 and then we run it with some eta, and so we get W1, W2. Let's just divide all these weights by eta. So look at this is equal to eta times W tilde 0, W tilde 1, W tilde 2, which are just the original weights divided by eta. So I can think about these weights as coming from the perceptron learning algorithm with eta, but I can also, if I will take these weights will come out from the perceptron algorithm with eta equals 1. Okay? So really, eta is meaningless in that sense, but there is one thing that has changed from here to here. One meaningful thing that has changed. The first set of weights. Okay, so here I started by W0, and here I started in this version of the algorithm where eta was 1, essentially. I started with the weights that were these weights divided by eta. Okay, so this is W0 divided by eta. And so actually, instead of asking why the perceptron algorithm, the success of the perceptron or the performance of the perceptron algorithm depends or does not depend on eta, which is a meaningless question, what we should really discuss is why it converges for any choice of the initial weights. Okay? And this is a slightly more subtle aspect. One thing before we kind of try to answer this question, at least qualitatively, we should consider why do we need initial weights at all? Why not set them to 0?
Well, then that whole expression will be 0.
Right, exactly. So we have to, in order to have a decision of the perceptron, we have to have some weights. If we set the weights to 0, it just doesn't. We don't know what it's deciding. So we have to start with some weights, but there is a point here that actually the initial weights don't matter. Now I'm not going to prove it to you. It comes out from the formal proof of convergence. But what you can see is that somehow when we see many examples, eventually our weights are really dependent on the examples. The initial weights somehow become less and less important in the content of the weights because we keep adding something. But this is not a proof. This is just some intuitive statement. Okay. Now the last comment, which is somehow more interesting from our point of view, is that this learning rule, it's nice. I mean, this learning rule can be interpreted if we think of this as a cartoon for biological learning in a network, right? We have a neuron which is learning to classify based on inputs. We have our output neuron, which is receiving inputs, and now let's think about this as a cartoon for biological learning, and now the W's are synapses. The strength of synapses, and our neuron is really adjusting its synapses to the inputs in order to learn to do something, then this learning rule has nice features. I mean, what it tells us is that Wi, t plus 1, the ith weight, is equal to Wi at time t plus some factor times y t plus 1 here, times y t plus 1 times x I t plus 1. So what does this mean? It means that the update to the synapse from this neuron to this neuron is proportional to the activity of this neuron, right? It's also proportional to the to the output. So it's proportional to the input and to the activity of the input neuron and the activity of the activity of the output neuron. Actually, we should really think about it a little bit more carefully. So this is not the activity of the output neuron. This is the desired activity of the output neuron. But you can also think about this as the activity of the output neuron times some signal, which is +1 if the neuron has done the correct thing. Okay, so let's think about this thing as W I T times X times WT times xt plus 1 transpose here t, and this will be the sign of this thing. This is what the neuron is really doing in response to the t plus 1 output, and then times some signal which I will call x. And x is really +1 if correct, and -1 if incorrect. Okay? So now if you look at it this way, the update is now indeed proportional to the activity of the input neuron, it's proportional to the activity of the output neuron, and then it's also proportional to some signal that's telling us if we're doing the right thing or the wrong thing. Right? So what biologically can be the source of such a teaching signal?
It can also be thought of someone as a supervisor of synapse that is very, very loud, and that it determines exactly the...
Actually, you know, I think I should. In fact, I wrote here something incorrect, because remember that we don't do a correction if the answer is correct. So it's not +1 if correct and -1 it's just a +1 if incorrect. You should have noticed this, right? I mean, if again the learning rule was if this is correct, you don't do anything. If it's incorrect, then you do this update. Okay, so
This is a standard Hebbian rule if we have another
exactly.
supervising synapse.
Well, not necessarily a supervising synapse. So we have a synapse which is undergoing a standard Hebbian rule, but with some teaching signal that is telling it whether it should update or not. And so now you're saying it should come from a supervising synapse, but in fact, another way that we often think about learning in the brain is that these things like this are modulated by neuromodulators. Okay, so perhaps there's a burst of dopamine in this brain area, and this dopamine is going to the whole network, to all these synapses, and it's just telling all of them at the same time whether they should update or not update. So this is a kind of a... No, it's telling you if you write now. So when you're presenting the t plus 1 example, if you're wrong, if you're right, you don't do anything. And if you're wrong, you need to update your synapses. So we should imagine here that the synapses somehow need to, all the synapses need to somehow know whether this was a case where we were wrong.
What is wrong and right?
So wrong is right is if we're dealing now with supervised learning. So suppose that I give you a reward if you did the correct thing, and I don't give you a reward if you didn't, or I give you a punishment if you did the wrong thing. Okay, so somehow the brain knows whether we have some signal coming to the brain which is telling the brain whether this was a good or bad. Well, the update rule is just an update rule for all the synapses going into this one particular neuron. But the update depends on some signal which we imagine is external to this how would you know? I mean, the whole context of supervised learning is a context in which someone is telling you what is the desired answer, right? So, okay, I don't want to. But you need something that's telling you whether you're doing something desired or not, and so. But this is common to most ways, to many cases where we think about supervised learning in the brain, where the brain is learning to do something while getting some signal which is telling the brain whether this is good or bad, that we imagine that there's some signal which is external to the network which is actually doing the calculation, and this signal is a signal which is signifying whether we're doing something good, desired, or something which is not desired. Yes?
So y or yt plus 1, is that like positive?
So this is a desired output for the t plus 1 example. And this is what appeared here in this room.
Right, but is that just 1 or negative 1, or is that a number, or is it a vector?
No, it's just 1 or negative 1. So in fact, I mean, I just wrote it this way. In a sense, this is if x is 1, meaning that this was incorrect, there's nothing here. I mean, it's 1. But I just wanted to think about this part as the output of the activity of the output neuron.
So that whole expression that you wrote there is equivalent to y. It's equivalent to the actual value of y.
This is exactly. This yt plus 1. What I mean by yt plus 1 is the desired output. But what I wrote here is the output of the network when you present to it the t plus 1 example, and it's still with the weights coming from the previous. The weights are the weights updated up to now. You present the next example, and this will be the output of the unit, right?
And here we're treating it as a binary.
But since it's a binary number, and we're okay.
Can't we say that if it's incorrect, it should be minus?
Well, no, no, but there's a plus here. There's a plus here. So this is actually, I should have put this x already. I should have put this x already here because this x tells us whether we should update or not, right? And so now I'm. Maybe it was 0 and 1.
0, then you get the same.
Okay, let's see. Let's do it. If yt plus, let's imagine that it's but no, I think we should think about this as 1 plus 1 and minus 1. And if it's plus 1, I think that I think that maybe I confused things a bit here. So let's do it carefully. So it's eta times 1 yt plus 1 times xit plus 1 times this signal that's telling us if we're doing the correct thing. And now what I wanted to do, the point is that this is not the activity of the output neuron, this is a desired activity.
It's desired or the change? Over there is the change in
No.
right?
No, I'm just writing this term. I'm just writing this term, and this term involves the desired.
Yes, but the whole term is the change. The delta.
Yes, that's right. But I'm just writing this term.
Times an external.
And my point is that I should put the x is 0 or 1 if correct and incorrect.
This is kind of
So okay, so what is x? Okay, so let's try to. So what is x? X is telling us whether so x is equal to 0 if w. Let's designate by y t plus 1 hat the activity, the output. In other words, this is the sign of wt transpose times xt plus 1. So this is what the neuron is spitting out when it's seeing the t plus 1 example. And then what does this mean? What does this mean? X is equal to 0 if yt plus 1 is equal to yt plus 1, and it's equal to 1 if yt plus 1 is equal to y to minus 1 t plus 1, right? Okay, so let's see what this means. So now, because of this, I can also say that when x is equal to 1, okay, so when x is equal to 1, this update, so this is delta wi t plus 1, right? This is the change in the synapse at step t plus 1. So when x is equal to 0, so I can also write this down as delta wi t plus 1 is equal to minus eta times y hat t plus 1 times xi t plus 1. Why? Because times this, I think the choice of the letter x here was not very good. So let's replace it. Let's call it S for or R for reward, okay? Or punishment. I don't know. So is this a reward or a punishment? It's like okay, E is good. L but E looks like the natural. You like Z? Okay. Z in our case is designating that we did something wrong. Okay, so it's like electric shock. So from Z. Okay, we're doing it now here. So here also let's replace it. Replace it by Z. So in any case, what I'm saying is that I could write it like this. Why? With this notation, and because if z is equal to 0, then it doesn't matter anyway, okay? And if z is equal to 1, then you see that y is equal to, the y hat is equal to minus the correct y, okay? So now we have our correct way of writing it. The update is proportional to the activity of the output neuron, the activity of the output neuron, the activity of the input neuron, and the signal, this electric shock signal. But going through, some neuromodulator perhaps in the brain. Okay, so yeah, so there is various evidence that neuromodulators affect local learning rules in synapses. No, but it's not the learning rate. It's the learning rate is there. Yeah.
When you put serotonin somewhere, that you increase the STP for a given.
I see. Yeah. This is also so, but this kind of goes beyond a very, very simple cartoon of learning. But it makes sense in more sophisticated situations of learning. It makes sense often that you want to adjust the learning rate. So as I mentioned, for the perceptron algorithm, the learning rate is not very important. But there are many other learning algorithms where I think that Z should be really thought of as, when you say learning rate, I think about something which is kind of changing slowly. It defines how you update based on many examples. Okay, but this is just a local, for each example, whether you update it or not. So I wouldn't think about it as describing learning rate. Okay, but okay, maybe you're thinking of completely other things. But I think that a general comment that the brain might want to adjust the learning rate in synapses makes sense in more elaborate cases of learning where when you become, I don't think we'll have time to discuss stochastic learning, unfortunately, in this course this year, but when you kind of learn based on examples, when you try to optimize some function, it's often the case that you want to start by doing kind of large moves when you're far from the optimum, and when you get closer and closer to the optimum, you want to start to update more with smaller steps. Okay, but this is again beyond this very simple example of learning. Okay, now I see that we won't start a new topic today, so I think what I will just mention to you now is one simple extension, very simple extension of this of what we've done. And this is just to ask what happens if we allow a bias in the perceptron architecture. So imagine that instead of having just W transpose times X and taking the sign of that, we allow some bias. And so now our architecture has, instead of having just n parameters in our network, we have one additional parameter. And so obviously, this is extending what the number. This can only increase the number of dichotomies that we can implement. And so the question is, can we say something about the capacity of this network? And the answer turns out to be extremely simple. And I think you mentioned the correct answer already last week. And this is that we can think about the n-dimensional, the case, so W is n-dimensional. We can think about our problem as a problem in n dimensions, where we have our examples x, mu, and we have our W, which is n-dimensional. But we can map it to another problem where the W's are n+1 dimensional, and where our examples are x tilde, mu. So mu is the index running on examples, right? Mu goes from 1 to p. So our examples are going to be n+1 dimensional vectors whose entries are simply the n-dimensional vector and 1. We'll always put 1 in the last in the dimension that we added to the input. And we'll think about our weights, our n+1 dimensional weights, W tilde, as the original weights. And here we'll call it Wn+1, but it really stands for the B. Why? Because the sign of Wn+1 transpose times tilde, sorry, W tilde transpose times x tilde mu is the sign of W times so this should have been x, W transpose x, this is this part, plus 1 times Wn+1. So you see that this is really exactly this computation, where Wn+1 is equal to B. And therefore, and now, so what is the situation? We have we mapped our problem with this calculation to a problem which is the previous type of perceptron we discussed, which does not have a bias. And all our examples are just, on this n plus 1 dimension, they are on the value is equal to 1. Now, if we choose n points which are in a general position in the n-dimensional space, then in the n plus 1 dimensional space, after adding this 1 here, this will be points in a general position. So I'm just saying that it's just the value. This is an n plus 1 dimensional vector. These are the first n entries, and the n plus 1 entries is just equal to 1. What would be a more clear way to write it down? Like a column vector? Squares of the... Okay. So just on this n plus 1 dimensional plane, all our points are at distance 1, height 1 from the origin. So my point is that if we have if we have p points in a general position in the n-dimensional space, these points will be in a general position in the n plus 1 dimensional space, and vice versa. And therefore, we can immediately use what we know about the capacity of the regular perceptron without a bias, and say that the perceptron with bias, let's call this with bias, for n dimensions and p examples is equal to the perceptron to the capacity without bias, which we know from Carvel's theorem, for n plus 1 dimensions and p examples. Okay, so having this extra degree of freedom in our architecture increases our capacity. The capacity of with n plus 1 is larger than the capacity of the regular perceptron with n plus 1 is larger than the capacity with n. But it's just like adding one more dimension. So it doesn't matter much. And I think we will end here.